Welcome to our comprehensive lesson on electrical science, focusing on DC circuits. Let's begin with DC, or direct current, circuits. Unlike alternating current, which periodically changes direction, DC provides a steady, unidirectional flow of electric current. Think of it like a river flowing consistently in one direction. Current moves from the positive terminal of the power source through the circuit components and back to the negative terminal. This is the type of current you'll find in batteries and many electronic devices. Passive components in DC circuits do not produce energy, but influence how electrical energy flows through the circuit. The primary passive components are resistors, capacitors, and inductors. Our first passive circuit component is the resistor. These components play a crucial role in controlling current flow, much like a water valve controls water flow. The fundamental relationship governing resistors is Ohm's law, V equals IR, where V is voltage, I is current, and R is resistance. When it comes to power dissipation, resistors convert electrical energy into heat, following the formula P equals I square R or P equals V square by R. Let's look at the types. Fixed resistors maintain a constant resistance value and are commonly made from materials like carbon film or metal film. Variable resistors, also called potentiometers, allow adjustment of resistance. Think of the volume control on your audio devices. Moving on to capacitors, these components act like tiny electrical batteries, storing energy in an electric field. Their storage capacity is measured in farads, though we typically work with microfarads, UF, or picofarads, PF. The energy stored in a capacitor follows the equation E equals half CV square, where C is capacitance and V is voltage. For practical applications, electrolytic capacitors are your workhorses in power supplies, while ceramic capacitors excel in high-frequency applications. A perfect example is your smartphone's camera flash. It uses a capacitor to quickly release stored energy for that bright burst of light. Inductors are our third passive component, storing energy in magnetic fields. Their inductance is measured in henries, H, and they resist sudden changes in current. The energy stored in an inductor follows E equals half Li square, where L is inductance and I is current. We have two main types: air core inductors for high frequencies and iron core inductors for low frequencies and power applications. A practical example is your car's ignition system, where inductors boost the low battery voltage to create the high voltage needed for spark plugs. Understanding basic electrical laws is essential for analyzing and designing DC circuits. These laws establish relationships between voltage, current, and resistance, providing foundational tools for circuit analysis. Ohm's law is one of the most fundamental principles in electrical engineering. It states that current through a conductor is directly proportional to voltage, assuming constant temperature. The formula V equals IR gives us a powerful tool for circuit analysis. Let's work through an example. If we have a 10 ohms resistor with 2 ampere current, applying Ohm's law tells us the voltage must be V is equal to 10 times 2 equals 20 volts. This relationship helps engineers design everything from simple circuits to complex electronic systems. The power law helps us understand energy consumption in circuits. Power, measured in watts, can be calculated in 3 ways: P equals VI, P equals I square R, or P equals V square by R. These equations are interrelated through Ohm's law. Consider this example. A 5 ohms resistor carrying 3 ampere of current dissipates P equals 3 squared times 5 is equal to 45 watts of power. This understanding is crucial for designing efficient electrical systems and preventing component overheating. Temperature resistance coefficients. The resistance of materials varies with temperature, which affects circuit performance. This phenomenon is especially significant in high-precision applications. Temperature significantly affects resistance in electronic components. The temperature coefficient of resistance, TCR formula, RT equals R naught 1 plus alpha delta T, helps us predict these changes. Here, RT is the initial resistance, alpha is the temperature coefficient, and delta T is the temperature change. For instance, if a 100 ohms resistor has a temperature coefficient of 0.004 ohms per degree Celsius and experiences a 25 degrees Celsius temperature rise, its new resistance would be 110 ohms. This understanding is crucial for designing temperature-sensitive equipment. In DC circuits, we work with two types of sources. Voltage sources maintain a constant voltage regardless of current draw. Think of a battery. Current sources, conversely, maintain steady current regardless of voltage, like LED drivers. While ideal voltage sources have zero internal resistance and ideal current sources have infinite resistance, real-world sources have limitations. Understanding these characteristics is crucial for proper circuit design. In series circuits, components are connected end-to-end like links in a chain. The key characteristic is that the same current flows through each component. The total resistance is simply the sum of individual resistances. R total equals R1 plus R2 plus R3, and so on. For example, if we connect 4 ohms and 6 ohms resistors in series, the total resistance is 10 ohms. This configuration is commonly used in voltage dividers and current limiting applications. Now, let's explore parallel circuits, where components share the same voltage across their terminals. Unlike series circuits, the total resistance in parallel follows a reciprocal relationship. 1 by R total equals 1 by R1 plus 1 by R2 plus 1 by R3, and so on. Let's work through an example. With two resistors of 10 ohms and 5 ohms in parallel, our total resistance would be 3.33 ohms. This is why your household electrical outlets are wired in parallel. It ensures each device receives the same voltage while operating independently. Kirchhoff's current law is based on the conservation of charge. In simple terms, what goes in must come out. At any node in a circuit, the sum of currents entering equals the sum of currents leaving, written as summation I in equals summation I out. Consider a node with incoming currents of 3 ampere and 2 ampere and an outgoing current of 4 ampere. Using KCL, we can determine that the other outgoing current must be 1 ampere to maintain balance. This principle is crucial in designing power distribution systems. Moving to Kirchhoff's voltage law, which states that the sum of all voltages around any closed loop in a circuit must equal 0, summation V equals 0. This follows from the principle of energy conservation. Let's visualize this with an example. In a loop containing a 10 volts battery and two resistors with voltage drops of 4 volts and 6 volts, KVL confirms that 10V minus 4V minus 6V is equal to 0. This law is essential for analyzing complex circuits with multiple voltage sources and components. Looking at the diagram, we can see how both KCL and KVL work together in a circuit. The arrows indicate current flow directions, and the voltage drops across components are clearly marked. This visual representation helps us understand how these laws apply in practical circuit analysis. Nodal analysis is a systematic method for finding voltages at various points in a circuit. The process involves 3 key steps. Choose a reference node ground with 0 voltage. Apply KCL to each non-reference node. Solve the resulting equations. This technique is particularly valuable when analyzing circuits with multiple branches and voltage sources, such as in power distribution networks. Mesh analysis focuses on calculating currents in closed loops or meshes within a circuit. The method works best with planar circuits, those without crossing wires. Following 3 steps. Define loop currents in each mesh. Apply KVL to each mesh. Solve the resulting equations. This approach is especially useful in motor circuit analysis, where multiple current loops interact. Now, let's explore a crucial circuit transformation technique, the delta star or delta Y transformation. Looking at the diagram, we can see 2 equivalent configurations: the delta, shaped like a triangle, and the star, shaped like a Y. In the delta configuration, 3 resistors connect between 3 nodes forming a triangle. In the star configuration, 3 resistors share a common central node, creating a Y shape. The fascinating part is that these configurations can be mathematically converted from one to another using specific formulas. This transformation is particularly valuable in 3-phase power systems, where engineers need to analyze and balance loads effectively. For example, in industrial power distribution, loads might be connected in delta configuration, but analysis might be easier in star configuration. The superposition theorem tells us that in linear circuits with multiple sources, we can analyze each source independently and sum the results. This principle is particularly useful in audio systems where multiple signals combine. Let's consider a practical example. In an audio mixing console, where multiple input signals combine to create the final output, superposition helps us understand how each input contributes to the final mix signal. If one input is 2 volts and another is 3 volts, superposition tells us their combined effect will be 5 volts, assuming the circuit is linear. Looking at the diagram, let me walk you through how this fascinating principle works. Imagine you have a circuit with both voltage and current sources. Instead of analyzing everything at once, the superposition theorem allows us to. First, turn off all sources except one. Replace voltage sources with short circuits and current sources with open circuits. Calculate the voltage or current you're interested in for that single active source. Repeat this process for each source. Finally, add all the individual results together. This theorem is invaluable in complex circuit analysis, though remember, it only works for linear circuits. Thevenin's theorem is like having a magic wand that transforms any complicated linear circuit into a simple equivalent circuit. For example, imagine a complex power supply circuit. Using Thevenin's theorem, we can represent it as a simple voltage source with internal resistance, making it much easier to analyze how it will behave with different loads. Looking at our diagram, this theorem states that any complex network of voltage sources and resistors can be replaced with a single voltage source, Thevenin voltage, VTH, a single series resistor, Thevenin resistance, RTH. To find these values, first, find VTH by measuring the open circuit voltage between your 2 terminals of interest. Then, find RTH by deactivating all independent sources, calculating the resistance seen from the terminals. This simplification is particularly valuable when you need to design maximum power transfer circuits, analyze loading effects, troubleshoot complex networks, and design power supplies. Norton's theorem is the current focus twin of Thevenin's theorem. Here's a practical example. Consider a current sensing circuit in a battery charging system. Norton's theorem helps us understand how the sensing circuit will respond to different battery states, from fully charged to discharged. The relationship between Norton and Thevenin equivalence is Norton current equals Thevenin voltage by Thevenin resistance. Norton resistance equals Thevenin resistance. This is particularly useful when working with current-sensitive devices, parallel connected loads, current amplifiers, and sensor circuits. Looking at the diagram, we see how any linear circuit can be converted into a single current source, Norton current, IN, a parallel resistance, Norton resistance, RN. The process involves finding in by short-circuiting the output terminals and measuring the current, calculating RN, which is identical to Thevenin resistance. The maximum power transfer theorem is crucial for optimizing power delivery in electrical systems. The theorem states that maximum power transfer occurs when the load resistance, RL, equals the source's internal resistance, RS. Mathematically, RL equals RS. When this condition is met, the power delivered to the load is Pmax equals V squared by 4 RS. The circuit operates at 50% efficiency. Half the power is dissipated in the source resistance. Looking at the diagram, you will understand this principle in depth. This principle is crucial in audio amplifier design, RF transmission systems, battery-powered devices, and sensor circuits. Let's examine RC, resistor-capacitor, circuits, which are fundamental in timing and filtering applications. The charging equation for a capacitor is VT equals V final, 1 plus e to the power t by RC, where V final is the voltage, T is time, and RC is the time constant. Looking at the diagram, we can understand the basic structure of a RC circuit. LC, inductor capacitor, circuits are fascinating because they create natural oscillations. The resonant frequency is given by F equals 1 by 2 pi under root LC. This principle is fundamental in radio receivers and transmitters, where specific frequencies need to be selected or filtered. We've reached the end of this video. Thank you for watching, and don't forget to like and subscribe for more tutorials on other exciting topics.